Today's lesson is a continuation of topic 4.2 and 4.3, which covers traveling waves and their characteristics. Okay, I'm going to skip over the understandings. We've talked about them in the past, especially for 4.2. Today's lesson is more about 4.3, and we're going to cover things about amplitude, superposition, and polarization, which is under the understandings in the upper left-hand corner. Actually, superposition I'm going to be moving into topic 4.5, which gets into standing waves. Okay. Formula-wise, there's three formulas here. The first two are basically not all that much for calculations because they're proportionals. To make them equal, I'd have to put a constant in front that we don't really worry about. The third one is Malice's law, which we will talk about. Okay, a couple of definitions first, okay? The first definition is intensity. And the intensity of a wave is the amount of power per unit area in the wave. Okay, so the more power I have in it, the more intense the wave happens to be. The closer I am to the source, gives me less area where all that energy is located. And as I go farther and farther out, there's less power. Okay, only because that power is distributed over a greater area. Second definition is polarization or polarized. Okay, a wave is considered to be polarized. Usually we're talking light when it is restricted to a single plane. So if my light is traveling in this direction, okay, from me to the camera, then for it to be polarized, my electric field, let's say, is only going to be traveling in one direction. It's going to oscillate this way, or maybe it's this way as it goes towards the camera, or this way as it goes towards the camera. Unpolarized light will have the electric field traveling in multiple planes. So one part of the light may be going this way, another part is going this way, another one is going this way. Okay, so that's unpolarized. By polarizing it, we're limiting it to just one plane. Okay, first off, intensity versus amplitude. By definition, okay, the intensity is the power per unit area. I know it says energy, I should correct that, but it's the power per unit area. For sound, intensity corresponds to loudness. How loud is the sound? For light, intensity corresponds mostly to brightness. How bright is that light? Okay, so energy, remember from simple harmonic motion, corresponds to the square of the amplitude. Okay, we have this formula that where total energy is 1/2 m omega squared amplitude squared. Okay, yes, IB uses x sub 0 squared to represent amplitude. Okay, therefore, since intensity is power and power is energy over time, then intensity is simply proportional to the amplitude squared. Okay. In terms of distance, okay, intensity is the amount of power per unit area. So assuming I don't lose any energy through the medium, that energy is going to get distributed over a greater area as we get farther from the source. Okay, and the surface area of a square is 4 pi r squared. And since intensity therefore becomes the energy power over area, intensity is going to be proportional to the square of the distance, inversely proportional to the square of the distance. Okay, so if you're ever in a concert and the noise is too loud close to the speakers, move farther away and that intensity will drop off reasonably quickly. Okay. Lastly, it's not part of the formulas, but let's look at amplitude versus distance. Okay, since intensity drops off with amplitude squared, and intensity is proportional to x to the minus 2, we solve for amplitude and distance, and so amplitude drops off with the distance. Okay, amplitude is inversely proportional to the distance from the source. Okay, and so these formulas also only apply to spherical waves like sound and light. Okay, doesn't really apply to a wave on a string. Light intensity, okay, this is really going to be discussed more next year, but I wanted to introduce it here just to put it in the back of your mind, okay? As described, the intensity of a wave is dependent on both area and amplitude. Light has a little bit of peculiarity because light is both a wave and a particle. Okay, this is the big discussion that Einstein and de Broglie basically solved. Okay, so since it's both a wave and a particle, the intensity is going to be dependent on the number of particles. We call those particles photons that impact the given surface. And the energy of a photon is given by E equals hf. E is energy. H happens to be Planck's constant. You should have run across this in chemistry, and I know you did. Okay, and F is the frequency of light. So I can increase my frequency, okay, and that will increase my energy or intensity. I can also increase the number of photons, turn on another light bulb, okay, for instance, and that would then also increase my intensity. So polarization is the big aspect of this topic 4.3. Okay, and polarized light may have been used as early as 900 AD by the Vikings. Okay, it's kind of like the first situation that we've encountered where somebody was aware of this possibility. Okay, it's still not proven. If you're interested, you can follow that link given. Many insects, however, can see polarized light, and it helps them orient themselves when they can't see the sun or need to be able to see through fog and stuff like that. Currently, we use light polarization in many modern technologies. Primarily, the one you're probably most familiar with is polarized sunglasses. Okay, but they're also used in 3D movies if you've ever gone to see a 3D movie, not the red and blue glass type. Okay, and in LCD displays, like the screen you're probably looking at right now. If you have a pair of polarized sunglasses at home, okay, put them on or actually hold them in front of you and look at the screen, okay, and rotate your polarized sunglasses 90 degrees and see what happens to your picture, okay. And so that's an indication of whether your screen is being polarized. We'll talk about that coming up, okay. So in general, light from most sources is going to be unpolarized. The light from most light bulbs, the light from the sun, meaning that the electric field and the magnetic field are in an infinite set of planes, okay? Light's traveling in all sorts of different directions, okay? But we can polarize light in several different ways, okay? For instance, if we reflect light off a plane surface, the light tends to be at least partially polarized. And that's why polarized sunglasses, by eliminating that reflection, cuts down on the amount of glare that you have. Okay, some crystals can polarize light. That's what the Vikings used. Okay, and various thin metallic strips can polarize light as well as molecular chains. Okay, so a polarizing filter is effectively what your polarized sunglasses are. We have a number of polarizing filters in class, and I hope to be able to demonstrate this to you. Okay, but first off, the light, this white rectangle, okay, is unpolarized. Let's describe it as unpolarized. This is just an animation, okay? But if I put a polarized filter in it, it cuts down on a lot of the light because it's only taking light that's in a specific plane. Okay, any light with a component that's not in that plane gets eliminated. So it looks a little grayer. Okay, if I put a second filter in, okay, that's in the same plane, then it really doesn't matter, okay? The first light's already in that plane. The second light's in that plane. It doesn't do anything. So it's just as gray as the first one. However, if I start to rotate that second one, okay, then it starts saying, well, less and less light, less and less of that component of the electric field will get through. Until I get to 90 degrees, okay? At 90 degrees, there's no component of the light from the first filter that gets through the second filter. So you end up with no light getting through, which if you took your polarized sunglasses, you may have noticed in terms of the rotation. Your screen should have gotten darker and lighter. Okay, and so We call that first filter a polarizer because it polarizes that light, okay, that was unpolarized to begin with. The second filter we call the analyzer, okay, because it allows you to analyze how much of that light is, what angle that light happens to be at, okay. And that brings me to Malus's law. Malus's law basically relates the intensity of the light after the polarizer and to the intensity of the light before a polarizer. Okay, and so it's given by this formula: I equals I0 cosine squared theta. I is the transmitted intensity, it's the after intensity. I0 is the initial intensity. Okay, and theta is the angle between the plane of the incoming light and the polarizer plane. So this applies primarily to polarized light already. So I0 is polarized, I is polarized on a different plane potentially. Okay, so when the incoming light is unpolarized, I0 is unpolarized, then the transmitted intensity is simply 1/2 I0. Okay, thank you.